Hello everybody, I'm Xinjue Hu from University of Ottawa and Beijing University of Post and Telecommunication. Today I would like to present my paper, 4DLFVD, a four-dimensional net-field video dataset. As we can see from the title, the main contribution of this paper is a net-field dataset, and I will list below why our net-field dataset is special from the others. The first thing we want to emphasize is that this site is specially for left field videos, and each group of videos is composite of multiple viewpoint streams rather than images. Although there exist many freely available left field datasets on the internet, most of them contain images. This is mainly due to the lack of appropriate capture equipment for left field videos in the market. Most existing commercial personal net-field cameras don't have the continuous shooting function and cannot be used to collect net-field videos. The second is all of our video data is obtained by real collection, not relying on software rendering or synthetically generated with algorithms. The camera matrix used for collection is designed and produced by ourselves, and we have introduced its detailed design in the paper. And the dataset has enough density of the number of viewpoints, which is 10 times 10. We believe it can support most types of applications and processing. At last, the sub-actual pixel resolution of the left field video is also high enough so that it can be displayed in high definition or generate a more detailed three-dimensional model. To the best of our knowledge, our dataset is the only one that meets all above requirements. Table 1 gives an overview of existing net-field datasets and highlights the benefits of our 4DLFVD dataset. As we can see, although Google's dataset in Citation 3 can collect realistic net-field video data, but the density of the viewpoint is too low, which limits many of its applications. The remaining datasets are mostly image-based or synthetic. Next, I will introduce our collection system. As we can see from the left figure, the camera matrix is composed of 10 times 10 1080p monocular video cameras distributed in the same direction and the same plane. We use the network switcher group to transfer all data inside the platform. The RTSP protocol is run on it to pump the 100 video sequences. A motherboard with the CPU and a clock control module are also integrated into the platform to manage and synchronize the whole system. At last, we can choose to pull the data from switch group and write them into the local storage unit, or we can stream them directly on the internet using RTSP. The right figure shows the appearance of the prototype system produced, and this is the size and weight. It looks a little bit huge and heavy, but after all, this is just a prototype for experiments. As for camera calibration, we don't choose to eliminate the production error by optical adjustment. We use software algorithm to estimate them so as to reduce the interference of the error in the subsequent processing. As we can see from the left figure, we also use the traditional checkboard scheme for calibration. The MATLAB's computer vision system toolbox is used to complete the process. An example of one camera's estimated camera parameters are given in the right figure. We also provide them in our dataset. In this page, we give a brief presentation to our dataset. The dataset provides 9 groups of net-field videos, as we can see from the figure and the table. All net-field videos in this dataset are collected in the public areas of 2 cities, Beijing and Shenzhen in China. All collection activities were legally allowed and officially permitted. Among them, 2 groups of sexes were collected in an indoor environment, and the rest of them were collected in an outdoor environment. The objects in the indoor videos include potted plants, furniture, and scenery outside the window. The objects of the outdoor videos include stone tablet on the square, pedestrians and vehicles on the road. The shooting time of all LF videos ranges from 30 seconds to 8 minutes, and the audio is removed to reduce size. The capture resolution of all video cameras is set to 1920 x 1056, and the frame rate is set to 24 fps. All streams are encoded by the standard HEVC codec set to the highest quality configuration. At the time of this presentation, the size of the dataset is about 38 GB. As you can see from the table, in addition to the information we mentioned above, we also provide a column of the message named the scene change. They are used to describe the motion of the video content. I will display 4 sequences one by one to demonstrate it. As we can see in the sequence cabinet, the object in the video hasn't changed at all, so it is defined as static. Then we see the sequence gate. Except for the change of the distant background, the foreground is basically unchanged, so we define it as slide. In the dramatic section roadside 1, the video content is a busy road. Many pedestrians and vehicles are moving, and some people even directly overlap all cameras when they walk through. For now, maybe you have noticed that most of the sequences in the dataset were shot at a fixed location. This is mainly because the current version of the prototype collection system is too heavy and difficult to move during shooting. However, we still try our best to provide a sequence to collect around the stone tablet on the campus of the university, as shown in the last sequence. In this sequence, the collection system will stop for a period of time every time it moves a certain distance, and then move on to the next time. Those poles can allow some algorithms, perhaps 3D modeling, to have more stable frames for processing, and it can also give the people pushing the device a breather. Okay, that's all for this page. At last, we use LF depth estimation as the example application to prove the validity of our dataset. We developed LF depth estimation algorithm, and the results for LF videos cabinet and depth are shown as an example in figure. The generated depth maps show that our dataset is capable of supporting the application of depth estimation and 3D modeling. If you are interested in our dataset, please access it on Attribute Dataport or GitHub. The website links have been listed on this page. We also welcome you to communicate with us at any time. Thank you.